This is my setup for calibrating and setting the signal generator up. I have a fairly good power meter here showing plus 15 dBm, the probe, and I'm also monitoring the voltage going to the Arduino. At the moment it's 4.48 and the output level is plus 15 dBm. You can't go over 5 volts, otherwise the Arduino input pin won't be very happy. I've adjusted the gain or the voltage levels going into the AD8307 detector and its intercept point. The intercept point is set at the most sensitive position, and I've adjusted the slope to around 50 millivolts per dB. So I go into my Arduino sketch where I'm going to display the dBm, and I put in a volts per dB factor, which is 0.05 or 50 millivolts per dB, and what effectively is the intercept point. And with those two figures, juggling them up and down a little bit, I'm able to have the display show plus 15 dBm, and then with a 20 dB drop in signal level show minus 5 dBm. So there's the there's the 15. I've got it upside down because my adjustments are on the bottom. If I switch in 20 dB, you'll see it go to minus 4.8. So the sketch is producing the right figures. Here's a quick look at the inside underneath the Arduino Mega 2560. Here's the AD8307 detector and an op amp there, an LM358. These are from my power meter kit, and these are connected to the output there. So that's a quick look at the bottom. This is the top of the signal generator. It's using a circuit board layout by Glenn McNeil as part of his project of his HF transceiver, which is the design I put in AR. The board contains the SI5351 phase lock loop module. Mounts the Arduino, which is upside down, some power supply components, LCD driver with adjustments, and some 2N5109s. The first one is a Class A amplifier, which boosts the 3.3 volts coming out of the module up to several more volts, and squares it up a little bit. And it feeds a 2N5109 emitter follower via a potentiometer on the front panel. The output of the emitter follower feeds these switched attenuators minus 10 and 3 minus 20 dB sections using a 3-pole two-position switch. The third pole in the center is earthed and helps improve the isolation. The potentiometer is not ideal and will be replaced by another attenuator, which is a true 50 ohm attenuator. So that's the top of the unit. Here's a look at the front of the signal generator. Tune control, encoder, the attenuator switches, power on off, and a scan switch. When I turn the scan on, it will scan from the contents of memory 1 to the contents of memory 2, in this case 10 kHz to 54 MHz. I can change the scan speed by changing the step size, as you can see, and you can see the output level changing. One thing to note is that the AD8307 is waveform sensitive. As we scan from 10 kHz up, the waveform tends to go from a square wave to a little bit of a sine wave as the harmonics get knocked back due to the frequency response of the amplifiers and the general layout. Overall, there appears to be something like about a 6 to 7 dB variation in signal. And under these tests, when doing these tests, you should always terminate the output in 50 ohms. Here you see the waveform coming out of the signal generator on the Crow as it sweeps from 10 kHz to 54 megs. You'll notice the peak-to-peak amplitude does not change very much. The change in dBm reading on the meter is caused by the waveform changing from essentially a square wave to a sine wave. With the sine wave, the harmonics are no longer there. The AD8307 is sensitive to waveform shape. The signal out of the generator hits the Crow using a piece of coax cable, and it's terminated at the Crow. If you use the probe, that will affect the results, particularly the frequency response. So for these sort of tests, you need a 50 ohm system. When scanning, I can stop the scan and it'll stop at the last frequency it reached, in this case 25 megs. There's 25 megs, and if I just go manually, I can just tune it to where I like, and it'll start from there again. Down to 1 meg there, 2 megs there, there's 1 meg, and I can go all the way down to 10 kilohertz if I want to, which is getting down there now. It's a little bit of sag due to the coupling capacitors, not quite passing 10 kilohertz quite so well. There it is there, and start up again. There we go. The output level of the signal generator across some of the ham bands does not actually change a lot, even though we've seen several dB changes from 10 kcs to 54 megs. If I go, for example, from the start of the 40 meter band and you watch the dBm meter down here, you'll see that it stays pretty right. We don't really start to see a drop off 0.1 of a dB at 7.270. So across the 40 meter band, if you're doing a test on a filter or something, it's staying within 0.1 of a dB or thereabouts. So here's the 80 meter band. Not much change at all, not until you get to 3.8, 0.1 of a dB, 4 megs, and so on. The signal generator puts out a square wave for most of its range. If you need a good clean sine wave, one way to do that would be to phase lock the sine wave oscillator to the output of this signal generator. The frequency accuracy of this generator is quite good. That way you don't need lots of band pass filters or low pass filters in order to generate a sine wave from the output of this device. This is a demonstration of the attenuator function of the signal generator. I've got it set at plus 10 dBm output, and I have the output of the generator terminated in a 50 ohm resistor. So I'll switch 20 dB in, minus 10.1. The next 20 dB is minus 10, and minus 9.9, and plus 0.2 for the minus 10. If I switch them all on, I get minus 35. Theoretically it should be minus 70. A power meter on the output shows around minus 60. So there's a 10 dB coupling that's going on through there. The reason for the minus 35 is that the AD8307 inside this case is picking up RF that's not coming from the attenuators. So that indicates better shielding is required. However, it's not a serious problem. Generally with a signal generator you tend to set it at a specific level, and I tend to use external attenuators in a lot of applications, better quality ones such as the HP. Being external, they have their own very well shielded enclosure, and in some cases you're looking at minus 100 dB in order to do some critical low level testing, which you would find difficult to achieve such attenuation inside a box like this.